So in section 4, we're going to work on evaluating and graphing logarithmic functions. Logarithmic functions are kind of a new idea, so you need to want to pay close attention to this. We want to talk about logarithm of y with base b. That would look like this. Logarithm of y with base b, or you might say log base b of y. Okay, so that's the way that would be written. Then there's a common logarithm. A common logarithm would be a logarithm with a base of 10, and it's on your calculator just as log. So when it's a base of 10, since we work in a 10 base number system, we don't bother writing the 10 in. And when you have a natural logarithm, that's a log base e, right? So we learned about Euler's number, and now we're talking about a logarithm with a base of Euler's number, and that's abbreviated as ln. So common logarithm and natural logarithm are on your calculators, on all the TIs, typically on most calculators, because they're the most commonly used. So just remember, a common logarithm is base 10, and a natural logarithm is base e. So in working with logarithms, we can simplify logarithms and use them to solve problems like this, where we've got a logarithm in a formula. And also logarithms are used to solve when our variable is an exponent. So in a problem like this, where we're talking about wind speed near the center of a tornado when d is the distance in miles that the tornado travels. So we could talk about speed related to the distance of travel, and we would need to understand logarithms in order to solve this. Okay, so we'll do this later at the end of the lesson. But in the meantime, let's start talking about logarithm with base b. So a logarithm of y with base b, as I already wrote for you, would be written this way. And you can see it logarithm base b of y equals x if and only if b to the x power is equal to y. So when you're looking at evaluating, thinking about the value of a logarithm, you're really looking at the base. And you're looking at the base and you want to think to yourself, this number here, to what power would equal this? That's what we have here. B, the base of the logarithm, to what power would equal y? Okay, so every logarithmic function, right, can be written as an exponential function, just like every addition problem could be written as a subtraction problem and vice versa. Logarithms and exponential functions, logarithmic functions and exponential functions, are inverses of each other, much as addition and subtraction and multiplication and division have that relationship. So if you look at this one, the other way to think of this item is 7 to what power is equal to 49, right? So I can think of it here just looking at the base going, oh, this number to what power equals that? That's x in this case would equal 2, right? Here we want to do 1/2 to what power is equal to 8? Well, that would be -3. And 8 to what power equals 512? And in this case, x would be equal to 3. So I've talked about rewriting them. So I've rewritten them here, and I got a little ahead of myself. I also evaluated them. Okay, so if it helps you, you can always rewrite the logarithmic equation as an exponential equation, and they have this inverse relationship. Okay? So practice this for a little bit. Do problems 10, 14, and 18, and then come back to continue the lecture. So now the book kind of slips this information by. All right, so I've pulled this section. It's not normally one of the things that I copy from the book to put into my lectures, but I don't want you to not notice this information, because these are a guide for you in terms of how you move forward later in this section and solve logarithmic equations and exponential equations to solve for x. Okay, so what I know, in fact, is that when I have this in my problem, I'm going to introduce this because you can see that this simplifies to just be x. Remember, x to the first power on one side of the equation is what our goal typically is if we want to solve. So when I have this, I'm going to do that. When I have this, I do that because it simplifies to be x. And when I have this, I do that because it simplifies to be x. And you can see that a logarithm with base b removes the base of a power. But the key is the bases have to match. Base of the power matches the base of the logarithm. When you have that relationship, they will cancel each other out. So you'll notice here, 7, I have a base of the power 7 and a base of the logarithm 7. That will simplify to just be x. Now here I don't have the same number, but I could rewrite 36 to be a power of 6, right? So this is 6 squared to the x power. And if I take a power to a power, I multiply the exponent, so log base 6 of 6 to the 2x power. Now the base of my logarithm matches the base of my power. So they cancel each other out, and this will just simplify to be 2x. Okay, so what this is leading you to understand is that here we just have these items and they can be simplified. As you work in solving equations later in this chapter, you'll have this on one side of an equation. And then you'll want to introduce this to both sides of the equation in order to simplify it to end up being this. Okay? So this is, right now, we're just using the inverse properties of exponents and logarithms. Later, what we're going to do is we're going to solve equations, and we need to use these tools in order to do that. So practice this with problems 29, 30, 33, and 34 to get a little practice, and then return to the lecture. So now we want to find inverse functions. So if you remember when we first learned about inverse functions, we switch the location of x and y. So if I do that here, x would be equal to e to the y plus 2 power. And over here, x would be equal to the log base 8 of y. And then I want to solve for y. So this introduces this new problem. Here y is an exponent, and here y is in a logarithm, and these are new things for me. I need to learn how to simplify this. So what I need to do is I need to go back to the concept that when I have b to the x power equals blah, 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 anything, then the way I get rid of this is I take a logarithm, base b of b to the x power, and I would do that to both sides of the equation. I don't have a full equation, so I'm just leaving a space here. Because these cancel, and I get x is equal to log base b of everything else. Okay, so this is the property I'm going to use. So what base logarithm? It always has to match the base of the power. So this has a base of e. So if I want to get rid of a power with a base e, I'm going to use a logarithm with a base e. So base e is a natural logarithm. I'm going to introduce that to both sides of the equation. And I do that because this cancels that, and I'm left with y plus 2. Now if I subtract 2 from either side, the natural log of x minus 2 will be equal to y. And that's the inverse of this function. So if I simplify this one, I have the opposite situation. I have a logarithm base 8, and I'm using the item that if I have a logarithm, I have a logarithm base 8, and I'm using the idea that if I have a logarithm base b of x equals something, I can exponentiate either side, and what do I make the base of the power? The same as the base of the logarithm. So a log b to the log base b of x power equals b to the everything else power. So I took both sides of the equation and I made them exponents on the same base. I do that because this will cancel, and I'll get x will be equal to b to the power of whatever else was on that side of the equation. So here I have a logarithm base 8. So then 8 is going to become the base of my power. So I have 8 to the x power is equal to 8 to the logarithm base 8 of y. Okay, and it stands to reason that if these two things were equal, then I can make them exponents on the same number. That must also be equal. I do that because this just equals y, because that cancels with that, and I just get y is equal to 8 to the x power. And this is the inverse of that. Okay, so you guys go ahead and practice that. Do problems 42 and 43, and then return back to our lecture. So when we talk about logarithmic functions, you see this is the graph of an exponential function. And you see the graph of the logarithmic function is its inverse. So we know that they are symmetrical around the equation y is equal to x. And what it does is it flips across the line and it rotates 90 degrees. So again, if we take a look at this, y is equal to b to the x when it's a decay function, right? When b is less than 1, you see this is what the graph of the inverse would look like. Same idea. It's stuff you already learned in previous sections about the relationship of the graphs of inverse functions. So this shows you in a growth function, and this shows you in a decay function. Remember, growth is when b is greater than 1, and decay is when b is between 0 and 1. So if we want to go ahead and graph logarithmic functions, what I want to do is I want to go ahead and put together an input-output table. You notice that these don't have h or k, so I'm not going to be translating it, meaning I don't have to move it when I'm done. But if you remember, right, when we did exponential functions, we always used inputs of -1, 0, and 1. So if this is an inverse, that means these are going to be the outputs, -1, 0, and 1. And I'm going to pick the base to the -1 power, that's 1/4, to the 0 power, that's 1, and to the first power, that's 4. Because log base 4 of 4 is 1, log base 4 of 1 is 0, and log base 4 of 1/4 is -1. If I had done an exponential function, I would have, for instance, if I had done y is equal to 4 to the x power, I would have picked, that's the inverse of this function, I would have picked -1, 0, and 1, and I would have gotten 1/4, 1, and 4. All right, so you can see this is the relationship. So remember, when you're picking inputs, we want to pick easy inputs. We're picking powers of the base. This is the base to the -1 power, the base to the 0 power, and the base to the first power. So then when I graph that, when x is 1/4, y was -1. When x was 1, y was 0. And when x was 4, 2, 3, 4, y was 1. And the graph comes up here and goes out that way. Now my asymptotes is now a vertical line. X is equal to 0 is my asymptote. Okay, so remember in exponential functions I had a horizontal asymptote. Because these are inverses, it's rotated 90 degrees, and I have a vertical asymptote. Over here I'm going to do the same thing. I'm going to pick powers of 1/5. So 1/5 to the -1 power is 5. 1/5 to the 0 power is 1, and 1/5 to the first power is 1/5. And when I go ahead and graph that, so this was a decay function, right? B is less than 1. So when x was 5, 1, 2, 3, 4, 5, I was at -1. When x was 1, I was at 0, and when x was 1/5, I was at 1. So this comes in this way and goes out that way. Okay, so couple different forms of how this works. Again, x is equal to 0 is my asymptote. Okay, you just want to go ahead and pick powers of the base in order to graph. Right? Now we have h and k, remembering that y is equal to a times the logarithm base b of x minus h plus k. So h is in parentheses with x, so what's being subtracted from x is 3. H is equal to 3. And nothing's being added on here at the end, so k is equal to 0. Now that I know what h and k are, I'm going to ignore them. I'm going to create an input-output table for log base 2 of x. I'm going to pick powers of the base, powers of 2, the -1 power, the 0 power, and the first power. And there's my input-output table. So when x is 1/2, I'd be at -1. When x is 1, I'm at 0. And when x is 2, I'd be at 1. And this is the graph without h and k. Since h was 3, I'm going to take each point and I'm going to move it 3 to the right. So 1, 2, 3, 1, 2, 3, and 1, 2, 3. These are my new points. And my asymptote is a vertical line at x is equal to h. So x would be equal to 3. And my asymptote 1, 2, 3, this is where my asymptote would go. Okay, so the shift in h moves the asymptote from being the y-axis to moving over to a new location. And we've graphed our function. One more example. In this case, h is -2, k is equal to -1. And I'm going to graph it without h and k. I'm going to pick powers of 4. So I'm going to pick 1/4, that's 4 to the -1 power. I'm going to pick 1, which is 4 to the 0 power, and I'm going to pick 4. When I graph this, at 1/4 I'll be at -1, at 1 I'm at 0, and at 2, 3, 4 I'm at 1. The graph comes up through here, goes out that way. And I'm going to shift it 2 to the left and down 1. So 1, 2 to the left and down 1. Sorry, let me change pen colors. 2 to the left and down 1. And then 1, 2 to the left and down 1. And 1, 2 to the left and down 1. So my asymptote is also moved. It moved 2 to the left. And you see my graph has shifted to the left and down just a little bit. If I put my asymptote in at x is equal to -2, there's my asymptote. Okay, so go ahead and practice graphing with h and k. Do 46, 47, 52, and 53. Come on back and we'll finish out the lecture. So now here's my problem. I want to go ahead and use this function. Speed is equal to 93 times the log of the distance d. This is a log base 10 plus 65. So now here it says, when I'm looking at this information, what's the important information? A tornado traveled 220 miles. So that's my distance, right? D is my distance. So 220 miles will go into my equation here in place of d. So I know that my speed will be equal to 93 times a log base 10 of 220 plus 65. So what I would do at this point is I would just go ahead and use my calculator to do a log base 10 of 220. So if I pull up my calculator, and I see here's a log base 10, so I'm going to do 220. Log base 10 is 2.342. Right? Then I'm going to go ahead and I'm going to multiply that times 93. I'm following order of operations. And then I'm going to add 65, and I end up with 282.85. So 282.85. All right, so remember a log with no number down here? That's a logarithm base 10. And this is how you work with logarithms. And as we continue on, we'll work more and more with some of the things we talked about, but most particularly with this information. Do not lose sight of this information that I sort of talked about here and then we practiced over here. We're going to be solving, as we continue on, solving exponential functions where the variable is an exponent, and solving logarithmic functions where the variable is in a logarithm, in order to continue on with all the different skills we're learning this semester.